EF0. Most people have no idea a tornado is already forming above their heads. Not the dramatic movie poster funnel twisting toward a farmhouse. Not the roaring monster that tosses semis like yard toys. Something quieter, something invisible. And once you understand what it's actually doing up there, 3 miles above the dog sleeping on the porch, above the grill smoke drifting sideways, above the kid on the bike who just turned the corner, you won't look at a green sky the same way again. It starts on a warm, humid afternoon somewhere in the American heartland. The air has weight to it, the kind of thick where your shirt sticks to your back the second you step outside, where the horizon looks slightly wrong but you can't say why. Families are firing up grills. A dog is asleep on someone's porch. Nothing looks wrong. Nothing feels wrong yet. But 3 miles up, the atmosphere is loading itself like a spring. Warm, moist air near the ground is rising. Cold, dry air from the west slides over the top of it like a lid on a pot. This is atmospheric instability. It is the universe quietly deciding it needs to rebalance something, building pressure with the patience of a thing that has all the time in the world. When that warm air punches upward through the cold layer, a thunderstorm erupts. Not the polite kind, the kind that turns afternoon blue into midnight green in 20 minutes. Cumulonimbus clouds explode upward at 100 miles per hour, towering 40,000 feet, higher than most commercial flights. Storm chasers who've spent 20 years watching this happen say there's a specific smell right before it turns. Something electric, something metallic, like the air is nervous. And deep inside that churning storm engine, the rotation begins. See, winds at different heights don't all blow the same direction. Near the ground, they push south at 20 miles per hour. Higher up, they scream from the west at 60. This difference, called wind shear, acts like invisible hands rolling a pencil between your palms. It creates a horizontal tube of rotating air, invisible, completely silent. That rotating tube doesn't care about you yet. An EF0, if one drops from this setup, is modest. Winds between 65 and 85 miles per hour, strong enough to strip shingles, snap branches, knock signs sideways. It might last seconds. Touchdown in a field with no witnesses, leave a swirl in the grass, and disappear. Most are never officially recorded. But here's what nobody says out loud. The EF0 is not the storm. It's the storm clearing its throat. Because once that rotating tube of air gets tilted vertically by the thunderstorm's rising column, and the updraft grabs it and pulls it upright, something in the storm's behavior changes, something fundamental. The storm stops being a weather event and starts being a system. And systems, unlike events, have the ability to grow. What happens when that rotation tightens and the cloud base begins to lower? The storm develops a beating heart of its own, and the atmosphere stops playing nice entirely. EF1. There is a specific type of thunderstorm that produces the overwhelming majority of significant tornadoes on Earth. Meteorologists call it a supercell, and it is not a normal thunderstorm that got big. It is a categorically different animal. A regular thunderstorm is self-defeating. Rain falling back through the updraft eventually strangles the storm from the inside. A supercell has solved this architecturally. Updraft and downdraft are spatially separated, warm air rising in one location, cold rain falling somewhere it cannot interfere. The storm sustains itself for hours, travels hundreds of miles, organizes, and it can develop the mesocyclone. A mesocyclone is a column of rotating air 3 to 10 miles wide, invisible from below, embedded inside the supercell's core. It forms when horizontal wind shear gets stretched vertically by the updraft, like pulling taffy upward, the column thinning and accelerating as it stretches, the way a figure skater pulls their arms in and spins faster. Storm chasers watching radar go quiet when a mesocyclone shows up clean and tight on the screen. They know what a well-organized mesocyclone can become. From the ground, the signs are subtle at first. The cloud base starts to lower in one area of the storm, forming a descending, ragged, rotating mass called a wall cloud, hanging below the main cloud base like something being lowered on a cable. Inflow winds near the ground pick up, rushing toward the storm as if something hungry is pulling them in. The pressure in your ears changes faintly. There's a rumble that isn't quite thunder, more bass, more continuous, like something enormous idling. An EF1 tornado drops from this system, winds between 86 and 110 miles per hour. Now we're past cosmetic damage. Mobile homes overturn, cars get pushed off roads, a well-constructed house loses portions of its roof structurally, not cosmetically, and whatever was under that roof is now exposed to what comes next. Trees that have stood for 50 years snap at the trunk. An EF1 is not survivable in its direct path without shelter. That point is worth sitting with. The funnel at EF1 is still tentative, thin, ropey, flickering in and out of visibility. The tornado is still negotiating with the atmosphere. What happens when the tornado stops negotiating and the rotation starts feeding on itself? The funnel thickens, widens, and finds its form, and the storm stops looking improvised and starts looking like it was built to destroy. EF2. This is where the tornado becomes recognizable. The image you've seen 100 times. The funnel is wide now, sometimes hundreds of yards across. It has stopped flickering and started owning the space it occupies. The color shifts depending on what it's pulling in. Pale gray if drawing clean air, deep brown when churning topsoil, nearly black when moving through a town and ingesting debris. The roar survivors describe, almost universally compared to a freight train, though most say that it doesn't fully capture it, is not the wind itself. It is thousands of individual projectiles orbiting the core at extreme velocity. It is structures being disassembled at speed. It is the pressure differential warping the air around the funnel into frequencies you feel in your chest before you hear them. EF2 winds run from 111 to 135 miles per hour. Well-constructed homes built to modern code and properly anchored suffer major structural damage. Entire roofs are removed as units. Exterior walls collapse inward. Mobile homes aren't overturned. They're destroyed and relocated, their contents distributed across the landscape. A car in an EF2 path doesn't get pushed off the road. It gets lofted. What most people miss about a tornado at this intensity is the pressure drop. As the funnel passes, it falls so rapidly, sometimes 10% in seconds, that the building essentially explodes outward. Windows don't break inward. They blow outward from the pressure differential. Walls bow. Structures that look intact from a distance have had their load-bearing joints sheared. Survivors describe hearing the house groan before it came apart. Not creak, groan, like something that already knew. The debris field around an EF2 is where the physics turns strange. Insulation threaded around fence posts, a framed photograph found 60 miles away, face up, completely undamaged. Playing cards embedded an inch into plywood. Storm chasers who've walked EF2 damage paths say, you eventually stop being surprised by destroyed things and start noticing the survivors. A china cabinet upright in a field. Doors still on their hinges, an egg unbroken. The EF2 is survivable. A basement works. An interior room on the lowest floor works. The tornado does not reach below grade. This is why the heartland doesn't lose entire towns every spring. The instructions work most of the time, but some days the atmosphere has more in it. Deeper instability, stronger shear. And on those days, the mesocyclone contracts, the rotation accelerates, and the tornado grows into something that makes the instructions feel less certain. What comes after EF2 is not a larger version of the same thing. It is the point where the tornado stops damaging buildings and starts erasing them. The difference between those two words is everything. EF3. Let's be clear about what EF3 means in practice, not severe damage. Entire stories of well-built structures collapse and are swept away. At EF2, you're talking about damage that can be documented, repaired in theory. At EF3, you're talking about a foundation slab with bolts sticking up and nothing else. The building was distributed across 2 counties in pieces that no longer resemble what they were. Winds between 136 and 165 miles per hour. Trains, actual locomotives weighing hundreds of tons, have been derailed and rolled by EF3 tornadoes. Asphalt has been stripped from road surfaces. The petroleum and aggregate literally peeled up and relocated. Trees in the path aren't just snapped, they're debarked. The bark sandblasted clean by the debris cloud. You can identify an EF3 path in a forest not by broken trees but by white ones, pale, stripped trunks standing in a corridor of silence. The debris cloud is the part photographs don't convey. The visible funnel is surrounded by a dense cylinder of airborne material, boards, glass, metal, soil, extending outward sometimes a quarter mile from the visible edge. The tornado you can see is encased in a tornado you cannot see. 2x4s have been driven through brick walls, straw found embedded in living trees, survivors injured by material that came from directions that made no sense because the debris field doesn't orbit neatly. It churns and ejects outward in patterns dependent on topography and the vortex's shape at that exact second. The 1974 super outbreak dropped EF3 equivalent tornadoes across 13 states over 24 hours. That is 148 tornadoes in a single day. Meteorologists studying it describe supercells interacting across state lines, sharing outflow boundaries, feeding energy back and forth. The atmosphere locked into sustained violence that outlasted daylight and continued through the night. A person in a basement beneath a well-built house has real odds of surviving an EF3. A person in a crawl space does not. A person in an interior bathroom on the ground floor is dependent on variables they cannot control. What's next door, which direction the debris field is moving, whether the building's frame holds long enough. The EF3 is where the margin between shelter types stops being theoretical. The EF3 still has a path you can map and a width you can measure. A damage surveyor can walk it, document it, and make sense of it. What comes next makes all of that feel completely beside the point. EF4. There is a moment in the growth of the largest tornadoes when the storm stops being a passing event and starts being a feature of the landscape. It moves slowly. It stays. It is wide enough and organized enough that people watching from miles away describe it not as something moving toward them, but as something that simply is. A permanent-looking column connecting ground to sky, rotating with a terrible patience, taking up more of the horizon than any weather phenomenon should occupy. That is the EF4, winds from 166 to 200 miles per hour. Well-constructed homes aren't just destroyed, they're swept clean from their foundations, leaving bare concrete slabs behind. The 2011 Joplin, Missouri tornado, rated EF5 at peak, tracked 22 miles and reached nearly a mile wide. In neighborhoods it crossed, investigators found foundations so clean they looked like the houses had been removed by machines rather than wind. No splinters, no debris piles. The material was simply elsewhere, distributed across miles of Missouri countryside in fragments. 162 people died in Joplin, despite sirens, despite warnings issued 24 minutes before the tornado struck, an eternity by historical standards, despite a population that knew tornadoes, had practiced drills, had survived storms before. They died because at this width and intensity, there is a radius of destruction from which no above-ground location offers meaningful protection. The debris field, the pressure dynamics, the suction vortices, small, intense subtornadoes that orbit the main funnel like satellites, extend the lethal zone outward in ways that no warning graphic fully communicates. Suction vortices explain why post-EF4 surveys find one house leveled while the house beside it lost only siding. From inside those houses, the difference is indistinguishable from random. This internal structure, sub-vortices orbiting the main funnel, is the part of extreme tornado research that keeps scientists working, because the EF scale alone doesn't capture it. You can survive an EF4 in a basement with overhead protection. People have. But the answer depends on variables you cannot control or know in advance. There is one level above this. Scientists have measured wind speeds inside it that approach what fluid dynamics models say should be a physical ceiling for atmospheric rotation. The atmosphere, apparently, never read those models. EF5. In the entire recorded history of tornado documentation in the United States, fewer than 60 tornadoes have been rated EF5, or the equivalent F5 under the older Fujita scale. 60. Out of hundreds of thousands of documented tornadoes since systematic records began, winds exceeding 200 miles per hour, by how much we often cannot determine because instruments capable of measuring these winds are routinely destroyed before they can transmit complete data. The highest radar-measured wind speed ever recorded inside a tornado was 318 miles per hour, captured by a mobile Doppler radar unit during the 1999 Bridge Creek Moore tornado in Oklahoma. That figure was not a guess. That was the sustained rotational velocity of the funnel itself. At EF5, the idea of a building as shelter becomes conditional in ways that should make you uncomfortable. Reinforced concrete structures have had walls collapsed. The 2013 Moore, Oklahoma EF5, 1.3 miles wide and 17 miles on the ground, struck elementary schools during the school day. Children survived because teachers covered them in hallways while the building came apart above them. 24 people died total, a number kept low by warning systems and the tornado tracking slightly south of the densest neighborhoods. The debris field of an EF5 defies easy description. Straw and grass blades are driven into tree trunks at depths measured in inches, not resting against bark but forced into the wood itself. A standard 2x4 pine board at 200+ miles per hour carries kinetic energy roughly equivalent to a small car at highway speed. The tornado carries tens of thousands of these simultaneously, along with bricks, steel pipe, fragments of cars, and the compressed remains of everything it has already passed over. It is, at its core, a self-loading ballistic system. There is no footage taken from inside an EF5 funnel by a human being. Armored instrument probes, built specifically to be placed in tornado paths, have been recovered from EF5 tracks. Some did not survive intact. The data that came back has helped extend average tornado warning times from under 3 minutes in the 1980s to over 13 minutes today. That gap of 10 additional minutes is responsible, by conservative estimate, for thousands of lives saved annually. What happens inside the vortex itself comes from modeling, from fluid dynamics at extreme conditions, and from instrument fragments that survived. The pressure at the center drops sharply enough to register on barometers miles away. The sound operates across frequencies humans feel in their chest before the ears register anything. Dogs and birds detect the infrasound minutes before human perception catches up. There are documented accounts of cattle moving, birds going silent in unison, 20 minutes before a tornado arrived. The EF5 is what happens when the atmosphere stops distributing its energy and concentrates it into a column less than 2 miles wide. A hurricane carries more total energy, but a hurricane spreads it. The EF5 focuses it with a precision that feels almost intentional. Almost. But even the EF5 describes a single storm on a single track. What happens when the atmosphere builds not one supercell but dozens, all interacting and feeding each other simultaneously across an entire continent? Outbreak level, April 25th through 28, 2011. 4 days, 15 states, 360 tornadoes. The 2011 super outbreak is the largest tornado outbreak in recorded history, and studying it reveals something the EF scale alone cannot capture. It shows what happens when the atmosphere stops producing individual storms and operates as a single integrated self-reinforcing engine of destruction across a continental scale. 11 separate EF5-rated tornadoes formed during those 4 days. Not one. 11. Alongside dozens of EF3s and EF4s tracking simultaneously across Alabama, Mississippi, Tennessee, Georgia, and Virginia. The Hackleburg Phil Campbell tornado stayed on the ground for 132 miles. The Tuscaloosa-Birmingham tornado tracked 80 miles through populated areas and was, at points, a mile and a half wide. Storm chasers who had spent careers intercepting major tornadoes described scenes they had no reference for. Multiple violent funnels were visible simultaneously on the horizon, the sky between them filled with rotation at every level. 321 people died. More than 2,000 were injured. What made 2011 different was the alignment of a slow upper-level trough, a deep low-level moisture plume from the Gulf, and a sharp wind shear boundary across the entire southeastern U.S. These created conditions where supercells became self-renewing. As one weakened, its outflow boundary triggered the next. The atmosphere was recycling its own violence across 4 days without a meaningful break. National Weather Service offices issued more tornado warnings in 24 hours than they'd typically issue in a full year. The warning system functioned. It was simply operating at limits it was never designed to reach. The science of tornadogenesis, the precise moment a supercell produces a tornado, remains incompletely understood. We can forecast favorable conditions. We can watch the mesocyclone tighten on radar. But we still cannot predict with certainty which supercells will produce tornadoes and which will die quietly. Two storms with identical radar signatures sometimes make entirely different choices. That gap is where researchers are still working. The tornado is not a solved problem. Every spring, the atmosphere starts loading again. Warm Gulf air pushing north, cold Canadian air pushing south, the shear building along the boundary. The question of what will happen is not fully answered in advance by anything we've built. And somewhere right now, in a layer of atmosphere you cannot see from the ground, the air has already started to rotate. The ingredients are gathering. The atmosphere hasn't decided what to do with them yet. It never tells you everything in advance. That's the part that should stay with you.